Hello, my name is Daniel Jilic, and for the second machine learning based assessment, my topic is YOLO V1. So before watching this video and studying this topic, you should, of course, have knowledge of how convolutional filters work, as well as the basics of convolutional neural networks, especially RCNN and fast RCNN, which I'll be comparing YOLO V1 to. YOLO stands for You Only Look Once, and it's an object detection model whose primary motivation was to be able to detect objects using a single pass rather than having a multiple pass approach like you saw with RCNN. So, for context, YOLO was first published in 2015, and at the time, the multiple pass approaches like RCNN were effective, but the biggest problem is that they're just slow. Having the separate passes for scanning, classification, and then any post-processing like non-maximum suppression just took too much time. And so YOLO was developed to be able to detect multiple objects in an image without any of these steps. So it has no loops, it doesn't scan at all, it's just a single pass. And because of that, it's extremely fast. In order to perform detection and classification in a single pass, the YOLO method passes the image through a convolutional neural network, and that network will split the image up into a 7 by 7 grid of 49 patches. And each patch detects the presence of an object or the lack thereof in the space it's responsible for, and it also predicts a bounding box and a confidence level for that object, or again, lack of an object. And importantly, the two final layers of the network are fully connected. And that means that each patch has access to the full spatial context of the image, in contrast to the previous scanning methods, which are only really analyzing the specific window that they're currently scanning. So finally, non-maximum suppression is used to ensure that each object is only handled by one patch of the 49 patches. And that's for the pretty common case that an object overlaps into neighboring patches, in which case you don't want to have multiple patches competing, which could result in the model labeling separate instances of an object when there's really just one large instance of that object. So the specifics of the architecture of the convolutional network that the YOLO model uses are simple. The model consists of a convolutional stack of 24 convolutional layers, followed by two fully connected layers. The first fully connected layer is a flattened layer with 4,096 nodes. And then the second and final fully connected layer is a 7 by 7 by 30 tensor. And so that 7 by 7 represents each of the patches in the 7 by 7 grid, so the 49 regions. And then for each patch, there are 26 possible categories, two bounding boxes, and two confidence values. And so that's where the 30 in that tensor comes from. So that means you have 49 possible objects detected, one for each patch, and 98 potential bounding boxes. But only the bounding box with the highest confidence value in each patch will be considered by the model, and the other will be discarded. And once you perform non-maximum suppression on those results, the model is finished, and you've detected and classified any objects in the image in a single pass through a convolutional stack. This diagram comes from the original paper published by Redmond et al. In 2015, and it just provides a visualization of the architecture that I just described. If you count up all the convolutional layers in the diagram, you'll find that there are, in fact, 24, as mentioned. And notice the two final fully connected layers. You can see that the first is the flattened 4096 layer that I described, and the final one is that 7 by 7 by 30 tensor that provides the final output of the model. You can also notice that most of the convolutional kernels are size 1 or 3, with the exception of the first, which is a 7 by 7. Now, let's compare how the YOLO version 1 performs against previously developed object detection models. At the beginning, I mentioned that YOLO was designed for speed. That was its primary motivation, but I didn't mention just how fast it actually was. Uh, Fast RCNN, for context, can process images at about 0.5 frames per second, while the first version of YOLO can reach a blindingly fast 45 frames per second. So it's extremely fast in comparison to the previously developed models. When it comes to accuracy, it still performs very well. If you look on the figure on the right, which also comes from Redmond et al., you can see the results of a comparison they did between YOLO V1 and Fast RCNN. Each pie chart shows the percentage of correct or not correct detections that the models made, as well as the type of the incorrect detection. Notice that the YOLO model had an only slightly lower correct detection rate of 65.5% compared to the 71.6% for fast RCNN, which is not a particularly lousy performance in comparison. But in particular, you can see that most of the incorrect detections that the YOLO model makes are localization errors, uh, which means that the object is present in the image, but the model has misplaced the bounding box where it shouldn't be. Compare that to the much higher ratio of background errors that the fast RCNN model makes. Uh, and that represents cases where the model mistakenly thinks that part of the background of the image is an object to be detected and classified. So that difference between localization and background errors makes up the bulk of the difference in the incorrect detections between the two models. The YOLO model may be accurate, and it is definitely extremely fast, but it does have some limitations or drawbacks. So remember that the model only predicts one bounding box per object for each patch in the grid. Since the grid is 7 by 7, that means that the YOLO model will never detect more than 49 objects in a single image. And there are certainly use cases where you may have a large number of objects in an image that you would want a model to detect. Additionally, since it only predicts one object per patch, that means it will fail in cases where multiple objects are tightly clustered in one section of the image. And so if a bunch of, say, small objects are all sitting and they fall in one patch in the grid, whether they're multiple instances of the same type of object or a bunch of different objects, the model can only make one prediction. So images like pills in a bottle or the contents of a pencil case, if they're small enough, and so all of these uh, different or separate objects fall in one patch, they may not be detected correctly by the YOLO model. And finally, I have a link here to the original paper that Redmond et al. Published in 2015 and that we saw a brief glimpse of in class. It's a really great summary of the work they did, and I highly encourage reading it to learn more detail about the model than the summary review that I've provided here. Thank you.